So if I start with this, let me still start with this thing, right? Computer was old stuff, right? It invented many years ago. And at that time, it was a mechanical one. 20,000 parts. And the cost is, at that time, 17,000. And it is even more expensive if you don't think of inflation than our laptop nowadays. Then the first computer is ENIAC. So what is the difference? It has 220,000 vacuum tube, right? And it is so big, 7,000 crystal dial. All of them are the discrete components, and it weighs 27 tons. Now, this was in the textbook, but nowadays you see it very often in the conference again. Why is that? Because now people talk about quantum computer. Nowadays, the quantum computer is just like this one, because we need to put it in the cryogenic refrigerator, which consumes a lot of power, right? Although the chip is very tiny, but it occupies a big room. So nowadays, people try to dream of what semiconductor went over in the last 8 decades or 7 decades. They hope that one day the quantum computer can be as small as our laptop, right? But still, you see there's a big improvement from the first differential machine to the first electronic computer. And it is very expensive, of course, $500,000 at that time, right? And 27 tons. But the most important breakthrough in the human being is actually the transistor invention. In the first computer, ENIAC, it used the so-called vacuum tube. Vacuum tube is not good because it's just like the light bulb at your home. Now you don't have it, right? The tungsten filament. They have very short lifetime because when you heat it up, the tungsten is going to evaporate. And very fast, they just broken. And then it doesn't work. Or maybe the flies go in and then short the circuit, and then the computer will die. And that's why it is called debug. If you know, I wonder if you know about why we call debug in the programming. That is because at that time, they really to find out where the bug went. They find the bug, and then they replace the vacuum tube, then the computer runs again. That's why it's called debug. And that is nowadays we call, when we debug our program, we call it debug. But with transistor, it's different. It's solid state. It's a solid state device. And the first invented in 1948, at that time they used germanium, right? Turned out it is not good. But this is still revolutionary. They got the Nobel Prize. But it's still not good enough, right? If you have the discrete component, even it's very tiny, even you can manipulate. I asked you to build a circuit with 1 billion discrete components. Let's say you are so small, you are a small demon, you can move the transistor around. You still cannot build the circuit. And the most important thing is come up with Jack Kilby, right? He and another person, unfortunately, I think if I remember correctly, passed away already in 2000. That's why that person cannot get Nobel Prize. They co-invented this integrated circuit. They found a way that you have a layout, and then you do this processing to the wafer. Then you naturally build up the whole circuit. Right? So this is very revolutionary. So another Nobel Prize. And indeed, they deserve that. They changed the world. Right, this is the first microprocessor by Intel, 4004. Now let's look at it. It's 1971. I bet all of you, or most of you, including me, was not born yet. It's 1 megahertz, 1,000 transistor, right? Feature size is 10 micron. What is 10 micron? I hope that you're very familiar with millimeter, micrometer, nanometer, and angstrom, right? Can someone tell me 1 millimeter is 10 to the power -3, or maybe I just put it in 10 to the power -3 meter, right? What is micrometer? Can someone tell me?
10 to the -6.
-6, thank you. How about nanometer?
Not -9.
Great. How about angstrom?
-10.
-10. Very good. Right? I need to make sure you know that because as an engineer, you do it a lot. Then remember 1 nanometer equal to 10 angstrom, okay, or 1 angstrom equal to 0.1 nanometer. This is the number we use very often. 10 micron is very large. You actually can barely see in your bare eye, I think. I never tried, but I think so. Okay. Right at this line. Okay, it's here. Now, what happened about how many years? 40 years, 50 years later. Still 2014, still pretty old, right? What do? It becomes this Broadwell dual core from Intel. 1.3 billion transistor. Remember what we had before? 1,000. 1,000 becomes 1 billion. So it is 1 million times more. Okay. Operating frequency is not that important. I will tell you, it's important, but you don't see that amazing change. It changed from 1 megahertz to 2 gigahertz. It's only 2,000 times 2kx, right? But you know, yeah, there's some technological limitation, but actually it can go higher. The problem is the heat. We'll talk about that later. But most important is the feature size. What is the feature size? Someone tell me what is feature size? What's the meaning of feature size?
Channel length of the transistor.
Okay, now you talk about channel. Thank you very much. You talk about channel length, right? And that is typically what we think about the feature size, right? But nowadays, when we go to very highly scaled device, channel length is no longer the dominating factor. I will talk about that later. But you're right, it is like the channel length. So it is the linear length. That's all we think about the smallest, let's just call it smallest pitch. Okay, the smallest feature. But the most important thing is it is the linear dimension. It means that in the x dimension, how much we can shrink it, right? So if we change from 10 micrometer to, let's say, 10 nanometer in the feature size, right? What is the reduction of the linear length? It means reduced by how many times? How many times?
1,000.
1,000. Yeah, thank you for answering my question. I know my question might be too trivial, but if you are paying attention anyway, actually you can make the class not that boring. Okay, reduced by 1,000 times. But what happened to area? How many times do we reduce the area?
1 million.
Excellent. It reduced the area by 1 billion times. And that is the magic of semiconductor. Looks like we're just reducing it slowly, 1,000 times, but we increased by 1 billion times, reduced by 1 billion times. Well, what's the big deal? Well, I reduce area by 1 billion times. It means that, right, of course, this is just a rough estimation. I can sell 1 billion times more chips for the same function. Correct? Well, I make it so small. So for the same function, for the same cost, right, or same cost, I can sell it. So I was selling for how much? Maybe you say 500,000 NEA. If I were able to do this for NEA, I reduce by 1 million. I'm selling for 50 cents per supercomputer, right? The concept is like that. And I really like this because it means Bill Gates and I are using the same cell phone. Even he is much, much richer than me. That makes me very happy. Second, well, maybe I can put 1 million more transistor on the same chip. And sell for the same price. Everyone is going to just dump away their computer because they want to change for something better. And that's what we have been doing, right? 4004, 8008, 802226, 386, 486, Pentium, Pentium 2, Pentium Pro, and all the way to Broadwell dual core, right? Our same price, we're paying Intel the same price in every generation, but we are getting something better and better, right? So I want you to appreciate this this scale of improvement. Okay. Any questions? Oh, did I? Okay. Now, we talk about Moore's law. You know about Moore's law, right? Moore's law is just that Morse say that, okay, based on 4 data points, if you do that in your thesis, your advisor is going to fail you, your 4 point and then draw a straight line, unless these 4 points are very expensive. And in this 4 points were very expensive. He showed that every 18 months, right, not exactly the same, right, the number of chips will double. So he predicts it's going to go up forever, okay? But nowadays, have you heard about the death of Moore's law? Anyone heard about that? Can explain to us what it is about?
Isn't it like contradicted by Dennard's scaling law? How there's a limit to how much we can shrink channel length?
Okay, good. Now, Dennard, actually what you're saying is exactly the what people think about the death of Moore's law. So we keep saying that let me maybe write this right, let's say per 18 months. Not exact, they keep revising, so don't argue with people. The most important thing, the keyword is exponential, right? In your interview, don't say that, oh, my professor told me it is 2x per 18 months. Really doesn't matter. The main point is go up exponentially. But then now if it cannot scale more. I cannot put more transistor in this way. Just like what Omid just said. The Dennard scaling fail because we cannot continue to do that. We are going to have gate oxide being too thin, a lot of tunneling, junction being too steep, a lot of band-to-band tunneling, a lot of leakage current, reliability issue, power consumption issue. We just cannot make it smaller and smaller. It's not because we cannot print it, it's just we don't get the advantage, which we'll cover a little bit later, but mostly cover in E222. So it is hitting a deadlock, right? So that is the death of Moore's law.
Professor, can you hear me?
Yes.
Can we also say that it's like the power wall?
Also power wall, yes. Good, good. I have not discussed power wall yet, but it is related, right?
Professor?
Yeah.
Does this account to short channel effects that you were referring to, the power and the power consumption and the stuff?
Yes, that is also related. So very good, right? I'm really happy that you all know this. But first, I put up the title, The Death of Moore's Law. Everyone say that, right? It depends on your philosophy, right? Let's say they are correct. Why they are correct, right? Let's say, let me just write down a few things, right? Fail of Dennard scaling. Right? Just now, Omi say that, right? And Cedric, you say power wall. What is power wall, right? And then what is power wall? Because too much leakage. And this is what Isa, right? I forgot your name. Too much leakage plus high frequency has too much increase the dynamic power, right? But power wall is not just that. When I talk about power, it's not about the data transfer power that I just told you. In Google, they spend 50% of the energy just to bring the data from DRAM to the logic unit, okay? Right. So we cannot just keep scaling and scaling like what we did before, okay? That is the so-called people say, oh, no more, we cannot scale more. You know, last time we had 22 nanometer. Now I go to 64, I cannot do a transistor with 14 nanometer. 7 nanometer, no. Or they even say, let's say you can go to 1 nanometer. How can you make a 5 angstrom silicon transistor? It's just 1 atoms, right? That's what they mean by that of power law, but of Moore's law, okay? But Moore's law has another interpretation. It's also about more function per chip. Well, do you really care about what the size of the transistor is? I don't think so. When you buy 80286, 386, 486, Pentium 2, you never really take out to see the size, right? All you care is that they tell you that, hey, I can do this operation 2 times faster than before. I can do this neural network 2 times faster than before. And that is Moore's law. And what is really changing our world? It's not about the transistor being smaller. It's about the CPU being more powerful. It's about it gives us more function, right? We don't buy because you put more transistor. I'm not eating the transistor, right? You give me 1 billion, so what? The point, I'm buying the function, right? So because of this, we say that it is still alive, right? This is just a debate, doesn't matter, right? It really doesn't matter whether it's alive or dead. For us, the most important is if we have the job and if our product can sell for money. If that's the case, I say it is still alive. Why? Because we still can put more function. What we can do is, for example, we can do heterogeneous integration. In the past, we don't have this technology. We can only have 1 chip. Now we can have chiplet. We put them together. Yeah, just now you say that power wall making a lot of power consumption because I have to transfer the data. NVIDIA was very smart. Remember, they do high bandwidth memory. How do they do that? They stack the DRAM on top of the CPU. And then they solve the problem. Isn't that they sell their GPU for higher price? Isn't that you do use their CPU to perform a more successful machine learning computation, right? So I want you to understand that even people say it is the death of the Moore's law. Well, you want to define this way, okay, you like death, okay, it's up to you. But for us, it is still alive. And I'm going to show you because I'm going to find a job in this area and use the salary to buy a house in the Silicon Valley. So it is still alive, right? So the main point nowadays is we want to do heterogeneous integration. We want to build the system, make it more complex, deliver more function. We don't just try to make the transistor smaller. In the past, it's really easy for engineer. Just make it smaller, then I have better function. That was the so-called, I don't know the golden time or whatever for the not scaling. Life is so easy, right? Every time a new project comes, VP say, next time deliver 2x performance. No problem. Everyone try to shrink it. Okay, implantation, make it shallower. Gate oxide, grow it smaller. Meets the reliability to 18 months later, we have it in the market. But nowadays, it's more than that. But we can still deliver. And don't you see that NVIDIA was doing that? Intel is doing that. AMD is doing that. Our life is still growing exponentially. That is the key point. Exponentially. In terms of function. Okay. So here, just to show the transistor count, right? We keep increasing the transistor, just use the Dennard scaling, but no, as what you all have said, or we just discussed, is the death of the Moore's law if you want to keep going up, right? But we do have more transistors because we put many chiplets together. We're still scaling them exponentially. Now, then what happened? Why we suddenly stop?